So one of the purposes of doing the long division and the synthetic division and looking at the remainder theorem and the factor theorem is to start considering the roots of a polynomial function. So let's do that. But in order to start, let's first talk about some of the properties of a polynomial, because we've been talking about quadratic functions, the roots of quadratic functions. We even mentioned the roots of a cubic function, a polynomial with a degree of 3. But there are certain things that apply to every single polynomial. So the first one, which I think you're going to realize is pretty important simply because of its name, is the fundamental theorem of algebra. And what this says is that if you have a polynomial, which we'll call f of x, of any degree, okay, as long as it's greater than 0, a polynomial of any degree, then we have at least one root in the complex number system, okay? So a polynomial f of x of degree n, so that can mean that the highest exponent is a 3, a 4, or 5, a 6, a 2, a 1, any degree n, okay? And by definition, a polynomial has n greater than 0, so we'll put that in here again. We have at least one root, or 0, in the complex number system. Okay, and just as a note, remember that a real number is also in the complex number system. The way that we would write that just says that the imaginary part is 0. So it would be written as a plus 0i. And the same thing is true of an imaginary number. So an imaginary number written as in complex form would just be 0 plus bi. So both of these would be in the complex number system, meaning that every polynomial has at least one root. Okay, so it may be imaginary, it may be real, it may have both an imaginary part and a real part. We've seen all of these. Okay, but we have at least one root. And then we have a second part of this, and that's called the linear factorization theorem. And the linear factorization theorem takes this one step further. It says a polynomial f of x again of degree n, where n is greater than 0, has n linear factors. In other words, what we're saying is that every polynomial has the number of factors that's equal to the degree, okay? And all of those factors are linear, okay? The number of roots equals the number of factors. The number of roots is equal to the degree of the polynomial, okay? So I'm going to write this down too, sort of as a sub. Okay, so this is really important because it'll actually help us find polynomials just by knowing the roots, okay? And we can also write a polynomial from the roots. We can write the polynomial as a product of linear factors. So let's do that. So there's one last thing that can be really important here, and that's that if a plus bi is a root, then a minus bi is also a root. So this is kind of like a separate, it doesn't go under any one of these theorems. If a plus bi is a root of a polynomial, then its conjugate, a minus bi, is also a root. And this may not seem obvious at first, but it actually makes perfect sense, right? If you remember when we were dividing complex numbers, we said the goal in division is not to actually divide. The goal is to get rid of the imaginary numbers in the denominator. So what did we do? We multiplied by the conjugate. And by multiplying by the conjugate, we wound up with a real number. Right? If you recall, a plus bi times a minus bi gives us a real number, a squared plus b squared. This is a real number. Now, why is this significant? It's significant because in our polynomial, in the original polynomial, 2x squared plus 3x minus 7, 8x cubed minus 6x squared plus 5x minus 1. All of these are polynomials. There are no imaginary numbers. So when we multiply our factors, we should never get an imaginary number. And the only way that's going to happen is that if one of our roots is complex, then if one of our factors is complex, or if one of our roots is complex, then when we multiply it by another root, we have to wind up with something real. And the way that that's going to happen always is to multiply it by its conjugate, okay? So a couple of other things if we're going to try and find the root from the polynomial from the roots, okay? If the factors, these are just things that you're remembering from what we've already done. So if the factors of a quadratic are x plus 3 and x minus 2, the roots are x equals 3 and x equals -3, and x equals +2, right? Okay, essentially what we've done is we've said, okay, x plus 3 times x minus 2 is equal to 0. So if you remember, we set each factor equal to 0, and then we solved for the root. So we got x equals -3 and x equals +2. So if we go backwards, what we're getting is the root, and we're trying to find the factors. So if we're trying to find the factors from the roots, then what we're going to do is we're going to set it equal to 0. So when given the roots, we can find the factors by setting it equal to 0. Okay, so let's just do a little bit of practice with this, okay? So first of all, we said that this is a quadratic, which automatically means it's a degree of 2, okay? So let's use this property to help us figure out polynomials from given roots, okay? Let's say, for example, so I'm just going to do a bunch of examples now. So I'm going to start numbering. And as soon as you feel like you've started to get the hang of it, then what you should do is try it on your own. So pause the video, try it on your own, okay? Okay, so given a polynomial of degree 2, with roots x equals -4 and x equals 5, we want to find the polynomial. So we're starting off nice and simple, okay? So what we want to do is we want to find, okay, well, what are the factors first? So the factors say, okay, take x equals -4 and x equals 5. And we're going to set them equal to 0. So in order to set these equal to 0, we're going to take the first one and we're going to add 4 to both sides. So we want to get rid of everything on one side. Keep your x's positive. So that's why we're moving the 4 over. So we're going to add 4 to both sides. And this gives us x plus 4 equals 0. Then we're going to do the same thing to the other one. We're going to this time subtract 5 from both sides because we want to get the 5 over to the other side. And this is going to give us x minus 5 equals 0. Okay, so our first step, it's really our only step, is to find the factors by setting x equals -4 and x equals 5 to 0. Okay, now we have our factors. Our factors are x plus 4 times x minus 5. Now this is going to become important only a little bit later, but I want to give you the terminology now. We call this the complete linear factorization. Okay, why do we call it this? Because each of these factors is linear. And we factored it completely. X plus 4 and x minus 5 cannot be factored any further. So it's the complete linear factorization. And then if we want to, we can multiply. So if it says simplify completely, then you want to multiply, okay? If it says you don't have to multiply, then you can leave it like this. So this is what f of x is equal to. We get x squared. Then we get minus 5x plus 4x minus 20, or x squared minus x minus 20. Okay, you only need to do this if it says to multiply. So in a lot of the cases, if I were to give you a quiz, we don't really care about multiplying. All we care about is the linear factorization. The reason why we typically don't care about multiplying is because the linear factorization is going to tell us more. It's going to tell us what the graph looks like. So over the next few videos, you're going to see how we can use this linear factorization to tell us what the graph of this polynomial looks like. So you only need to multiply if it asks you to. Just like in quadratics, we said that when you complete the square, the factors actually tell you more. The same thing is true for all polynomials. Okay, let's take another polynomial. So let's do another example. This time, we're going to say, given a polynomial of degree 3, with the following roots. Let's say that you're given the root x equals negative 2, and you're given the root x equals 3 minus 4i. Find the polynomial. And I'm going to put in parentheses here and multiply. So we're not going to typically, on a test or something, particularly with polynomials greater than degree 3, I'm not going to ask you to multiply. Polynomial of degree 3, maybe. But it's not, the multiplication is just here. I'm doing it so that you can see how things work, okay? Now this is where the linear factorization theorem comes in. Because if you notice, this has a polynomial of degree 3, but we only have 2 roots, and we should have 3 roots. So the question is, well, what's the missing root? So a polynomial of degree 3 should have 3 roots. That's why the degree is important, because that'll tell you, are you missing any root? So this degree is really important, but other than that, other than knowing how many roots you have, it plays no role in finding the factors, okay? So what do we do here? Well, let's go back to what we said earlier. We said that if a plus bi is a root, then its conjugate also has to be a root. So that means that by knowing that 3 minus 4i is a root, we also know that its conjugate is a root. X equals 3 plus 4i is also a root. Every complex root every complex root's conjugate is also a root. Okay, so now what we're going to do is we're going to find the factors. Okay, so in order to do a complete linear factorization, we must find the factors. We find the factors from the roots. How do we do that? We set each of the roots equal to 0. So we're going to take x equals -2. We're going to take x equals 3 minus 4i. And we're going to take x equals 3 plus 4i. Now we have 3 roots, which is going to give us our 3 factors, okay? And for the first one, we're just going to add 2 to both sides. And we get that x plus 2 is equal to 0. So that's one root. And you're going to see that you don't have to do this every time, right? At a certain point, you're going to become familiar with this. You're going to say, okay, x equals -2 is the root. So x plus 2 is the factor, because we know that the sign just switches. Why does the sign switch? Because we're adding it. If it's a negative, we have to add it to get it to both sides. We have to do the opposite, okay? And same thing with these. You're going to sort of see at a certain point, oh, wait, this is what the factor is going to look like. So you don't always have to set up these equations. It's a good idea to do it in the beginning until you get used to it. So we have x equals 3 minus 4i. We need to set it equal to 0. How do we do that? Well, we have to subtract 3 and add 4i to both sides. And with the other one, while we're here, we're going to subtract 3, but we're going to subtract 4i from both sides. Which gives us our 2 remaining factors. Our 2 remaining factors are x minus 3 plus 4i. We have an equals 0. Then x minus 3 minus 4i equals 0. So what are our factors? Well, we don't worry about the equals 0. That's not a factor, okay? It's just like up here. It's just the x plus 4. It's just the x minus 5, okay? That equals 0 comes from solving for the roots. So same thing here. We have x plus 2 as a factor. We have x minus 3 plus 4i as a factor, and we have x minus 3 minus 4i as a factor. Okay, so let's write down that polynomial then. So the complete linear factorization would be that f of x is equal to x plus 2 times x minus 3 plus 4i times x minus 3 minus 4i. Okay, so in this particular problem, I'm multiplying. And the reason I'm multiplying is to help you see why the conjugates both have to be factors, okay, or both have to be roots. So the easiest way to do this is to multiply the complex roots first, meaning the ones that you see I in. And the reason for that is we're going to eliminate the imaginary numbers by doing this. So if we can do that faster, it's going to be less multiplication. And since in multiplication the order doesn't matter, we can do that. Again, you don't have to do this. It just makes it less work in the end. So what does this mean? This means that everything in the first set of parentheses gets distributed to everything in the second set. So this x is going to get multiplied by x, -3, and -4i. This -3 is going to be multiplied by x, negative 3 and negative 4i. And this positive 4i gets multiplied by x, negative 3, and negative 4i. So everything in the first set of parentheses gets distributed to everything in the second set. So let's do that. And we'll do it relatively slowly. Some of you, I noticed in your problem sets, you're skipping steps. And by skipping steps, it makes it very hard to see where you go wrong. And that's important because so much of math is about the way that we communicate our work and our ideas. And if we can't see where something went wrong or where it went right, then you're not communicating well. Okay, so we have x plus 2. That's just going to get carried down. That comes from this x plus 2 up here. And then we can distribute. So x times x is x squared. Then we have x times negative 3, which gives us a negative 3x. And then we have x times negative 4i, which gives us a negative 4i x. Then we distribute the negative 3. So negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. And then negative 3 times negative 4i gives us a plus 12i. And finally, we're going to distribute the 4i. So we get plus 4ix. Then we get minus 12i. And then we get 4i times negative 4i, which is negative 16i squared. Now notice what happens here. And this will always happen. If it doesn't, then you did something wrong. Any part that is imaginary, that has an imaginary part to it, will cancel. So the first one that we come up to is negative 4ix. Notice there's a negative 4ix, but there's also a positive 4ix. They cancel, which makes sense. Our final polynomial should not have any i's in it. The next imaginary part that we come up to is this 12i, but there's a negative 12i, so that cancels. And our last one is negative 16i squared. But remember, a negative 16i squared becomes a positive 16. I squared is negative 1. So if we write this again, and again, you can combine steps, just be careful not to skip too many. What we're left with here is x squared minus 3x minus 3x plus 9 and then plus 16. Because negative 16 times negative 1 gives us a positive 16. Now let's combine like terms. X plus 2 is times x squared minus 6x, and then 9 and 16 is plus 25. So notice what happened. We don't have anything imaginary anymore. So this is the complete linear factorization up on top, but when we multiply to get our polynomial in standard form, we completely get rid of anything that's imaginary. Okay, now we just do distribution again. So everything in the first set of parentheses gets multiplied by everything in the second set, meaning we're going to multiply the x by the x squared, the x by the negative 6x, and the x by the 25, and then the 2x squared, then 2 times negative 6x, and then 2 times 25. And when we do that, we get x cubed, then x times negative 6x is negative 6x squared, and x times 25 gives us plus 25x. Then we get 2 times x squared, which is 2x squared, then 2 times negative 6x, which is negative 12x, and then 2 times 25, which is plus 50. And if we combine like terms, this gives us x cubed. Then we have a negative 6x squared and a positive 2x squared, so minus 4x squared. Then we have 25x and a negative 12x, which gives us a plus 13x, and then plus 50. And this is our polynomial. And you can see why I typically wouldn't say multiply everything, because it is very time consuming. Okay, so I'm not going to do that regularly on a test, but you should be prepared for it. You certainly should have the algebraic ability to do this. So if that's something that you're having trouble with, you should definitely come to my office hours. Okay. Do we have any questions? Of course, I'm talking to a computer. Sorry about that. I forgot. Okay. If you have questions, send me an email. Okay, let's do another example, and I'm not going to do any more multiplication, so you should really study this. Take your time with it. Now we're just going to do a couple where I give you the polynomial's degree and I give you the roots, and you find the complete linear factorization. So let's say given a polynomial of degree 5 with the roots x equals 6, x equals 2 minus 7i, and x equals negative 5 plus I. Find the polynomial. Okay, you don't have to multiply. So you should consider pausing the video and seeing if you could do this one. So the first thing is we see 3 roots here, but it's a polynomial of degree 5. So what that 5 tells us is we have 5 roots. So what are the missing roots? Well, we have x equals 2 minus 7i. We know that x equals 2 plus I is also a root. The complex conjugate is a root because we know when we multiply with the complex conjugate, we're going to get something real, and we have to get something real. That's the first missing root. Now we see another complex root. And in order to get rid of this, of the imaginary number in this way, we need the complex conjugate of this. So the second missing root is negative 5 minus I. Okay, so notice conjugate means just the sign in the middle changes. Okay, so we know all of our roots now. And by the way, you would not be told that you have a polynomial of degree 5 and you can't find 5 roots. We're not doing that, okay? So in all of the problems you get, you will be able to find all of your roots. So let's take each of these. And again, some of you will be able to go straight from here to the linear factorization, but let's do it so that we get accustomed to it, and for anybody who's still kind of on the fence and they're not sure. So we have x equals 6, x equals 2 minus 7i, x equals 2 plus 7i, and then we have x equals negative 5 plus I, and we have x equals negative 5 minus I. So we're going to go and we're going to find each of the factors. So here we have x equals 6. We want to get the 6 over to the other side, so we subtract it from both sides, giving us x minus 6 is equal to 0. Okay, in this next one, we need to get the 2 minus 7i over to the other side. So we subtract the 2 and we add the 7i. which gives us x minus 2 plus 7i. So notice everything changes sign. And the next one, it's almost the same thing, except instead of adding 7i, we subtract. So we have minus 2 minus 7i, and then minus 2 minus 7i, giving us x minus 2 minus 7i is equal to 0. And then with the last two, similar. Here we have to add 5 and subtract I from both sides. Which gives us x plus 5 minus I. And then finally, the last one, we have to add 5, and this time add I to both sides. Okay, what we're doing is essentially going backwards. We're saying, okay, we have the root. What did it look like as a factor when we were trying to find that root? Okay, so now we have all of our factors. So remember, the equals 0 is independent. That's just how we found the factor. So we have x minus 6, x minus 2 plus 7i. These are our factors. X minus 2 minus 7i, x plus 5 minus I, and an x plus 5 plus I. So if we want to find the linear factorization, we just write this all out. X minus 6, x minus 2 plus 7i, x minus 2 minus 7i, x plus 5 minus I, and x plus 5 plus I. This is our polynomial. And it's a good habit to say f of x equals. So it's clear that you're telling us this is the polynomial. Okay, let's do one more. Given a polynomial of degree 7, let's say, with roots x equals negative 2 plus 8i, x equals 7, x equals negative 10, x equals 3 minus 6i, and x equals 5. Okay, so we have 5 roots right now, but we need 7, okay? So we're missing 2 roots. What are the 2 roots we're missing? Well, look at your complex numbers. You're missing the complex conjugate. X equals negative 2 minus 8i would be one missing root. And x equals 3 plus 6i would be our second missing root. Okay, and I apologize, I didn't find the polynomial here. So now we have 7 roots. Okay, so a polynomial with degree 7 has 7 roots. That's how we knew that some were missing. And your missing roots will always be complex conjugates of complex roots that you already have, okay? Because otherwise you wouldn't know what those roots are. You can't, we'll be talking in one of the future videos how we can take guesses about the roots and then test them. But here, we don't know what the original polynomial is, so we can't take a guess, okay? Okay, so now let's set up our roots and set them equal to 0 so that we can find the factors. And this is a little tedious, which is why the more practice you get, you don't have to do this anymore, okay? You'll be able to just know the factors just by looking at it. So we have x equals -2 plus 8i. And we have x equals -2 minus 8i. Then we have x equals 7. We have x equals -10. X equals 3 minus 6i. X equals 3 plus 6i. And x equals 5. And all we're going to do is take each of these and set it equal to 0, just like we did before. So in this first one, we have to add the 2 and subtract the 8i. Add the 2, subtract the 8i. Which gives us our first factor. X plus 2 minus 8i. And the second one, it's similar. We have to add the 2i. We have to add the 2, but this time we're adding the 8i. Which gives us our second factor, x plus 2 plus 8i. And the next one, it's pretty straightforward. We need to get rid of the 7, so we subtract it. And we get our third root. X minus 7 is equal to 0. Sorry, our third factor. In the next one, we just add the 10 to both sides. And we get the fourth factor. X plus 10. In the next one, we have to subtract the 3 and add the 6i. Giving us our fifth root. The next one, similar. We subtract the 3 again, but this time we subtract the 6i. Giving us our sixth root. And then finally, in that last one, we have to get the 5 over to the other side, so we subtract 5 from both sides, giving us x minus 5 as our last root, as our last factor. So we have 7 factors. Double check. 1, 2, 3, 4, 5, 6, and 7 factors. So now we just write it out as the complete linear factorization. So we have f of x is equal to x plus 2 minus 8i. The order does not matter. Remember, this is all multiplication, so which factor you put first is completely up to you. Notice all of your factors have an x. None of them have a 7. None of, in this case, actually, there is a 7. That's coincidental, but the degree is independent of the factors. All the degree tells you is how many factors there are. And you can see why in a problem like this, I would not ask you to multiply. That would take you a half hour. Okay, so this is how we can find the polynomial given the roots of that polynomial. We have to know the degree because we have to know how many roots there are. And then That's going to tell us if there are any roots missing. The missing roots will always be conjugates, complex conjugates. If you can't find it using a complex conjugate, then you can't do the problem. Okay? And that's it for this one.